What do you get when you combine the vision of a dragonfly, the grasping arms of a mantis shrimp, and a circular mouth with tooth-like plates arranged radially? You get Anomalocaris, Earth's first true apex predator that dominated Cambrian seas 500 million years ago. This creature reached lengths of up to 15 inches and possessed compound eyes with at least 16,000 lenses, with estimates suggesting up to 24,000 talons, giving it nearly 360-degree vision that could spot prey from incredible distances. But here's the twist that's revolutionizing paleontology. Everything we thought we knew about how this ancient terror hunted was completely wrong. The path to understanding this predator began with a scientific mystery that would puzzle researchers for nearly a century. 3 bizarre fossils sat in museum drawers for nearly a century, each labeled as completely different creatures that paleontologists could not quite understand. These specimens represented one of the most confounding mysteries in paleontology, defying classification and frustrating researchers who encountered them. The confusion began in the late 1880s when Richard McConnell of the Geological Survey of Canada discovered the first fragments in the Stephen Formation of British Columbia, though the significance of his find would remain hidden for decades. In the early 1900s, scientists believed they had identified 3 distinct Cambrian creatures from the Burgess Shale. The first appeared to be the segmented abdomen of a prehistoric shrimp, complete with what looked like jointed segments and swimming appendages. Joseph Whiteaves, studying these curved, segmented structures, confidently classified them as belonging to an ancient arthropod he named Anomalocaris, meaning strange shrimp. The second fossil puzzled researchers even more. Charles Doolittle Walcott discovered what he interpreted as a circular jellyfish with a distinctive ring-shaped body, which he named Peytoia. The third specimen resembled some kind of sea cucumber or other soft-bodied marine animal that did not match any known species from the Cambrian period. Each fossil presented its own perplexing characteristics that made proper identification nearly impossible. The supposed shrimp abdomen had no head thorax or legs attached, despite being beautifully preserved. Whiteaves found himself studying what appeared to be a complete appendage system, yet it belonged to no recognizable body plan. Meanwhile, Walcott's jellyfish defied conventional understanding. Instead of the expected tentacles and soft tissue, this creature possessed a mouth lined with sharp triangular teeth arranged in a perfect circle. The third fossil, initially thought to be some kind of sea cucumber, displayed unusual ridges and structures that did not correspond to any known echinoderm or soft-bodied invertebrate. The preservation bias in the Burgess Shale created additional obstacles for researchers trying to understand these creatures. The fossilization process favored harder structures like appendages, mouthparts, and chitinous elements, while the delicate body tissues remained completely hidden from view. This selective preservation meant that isolated specimens of hardened body parts were being described as separate species when they actually belonged to complete animals whose soft tissues had simply failed to fossilize. Scientists kept discovering the most durable parts first, the grasping appendages, the circular toothed mouth, and various body segments, but the connecting soft tissue that would reveal the complete animal stayed buried in the rock matrix. Decades passed as these 3 fossils defied all attempts at proper classification. The paleontology community grew increasingly frustrated with specimens that seemed to break the rules of Cambrian life. Each new discovery only added to the confusion rather than clarifying the picture. Researchers proposed various theories suggesting the appendages might belong to different arthropod species, or that the circular mouth represented a new type of Eonidarian. Some scientists even wondered if these fossils represented preservation artifacts rather than actual biological structures. The breakthrough began in 1966 when Harry Whittington of Cambridge University launched a comprehensive revision of the Burgess Shale fossil record. Working alongside his students, Derek Briggs and Simon Conway Morris Whittington began methodical detective work that would transform paleontology's understanding of Cambrian life. In 1979, Briggs made a crucial observation. He recognized that the fossils previously identified as shrimp abdomens were actually appendages, possibly belonging to a giant arthropod he could not yet identify. The evidence slowly mounted that something much larger and more dangerous was hiding in plain sight. In 1981, Whittington and Briggs examined specimens from Walcott's original collections and made a startling discovery. They found appendages directly attached to specimens bearing the circular mouth that Walcott had called patoia. The realization hit them these were not three separate animals at all, but components of a single massive predator. When Whittington and Briggs published their findings in 1985, they revealed that all three mysterious fossils were actually body parts of Anomalocaris, a 24-inch predator that would completely rewrite our understanding of Cambrian ecosystems. This complex history of misidentification would become a well-documented case study in paleontological methodology. With its true form finally assembled, scientists could begin investigating the remarkable capabilities of this reconstructed predator. The visual capabilities revealed through careful reconstruction were nothing short of extraordinary. The paired eyes recovered from the Emu Bay Shale in South Australia measured 1.18 inches wide, making them larger than any other animal eyes found in the same geological formation. These massive stalked eyes contained at least 16,000 individual ommatidial lenses in a single eye, with estimates suggesting the total could have reached 24,000 lenses per eye when accounting for the complete visual structure. The compound eyes rivaled the vision of modern dragonflies, which possess up to 28,000 lenses in each eye and represent some of the most sophisticated visual systems in the animal kingdom today. This made Anomalocaris vision exceptional even by modern standards, as only dragonflies among contemporary arthropods achieve comparable or better resolution. Each lens in Anomalocaris followed the hexagonal arrangement characteristic of arthropod compound eyes, creating a honeycomb pattern that maximized visual coverage while maintaining structural integrity. This configuration allowed the predator to process visual information from thousands of individual photoreceptive units, simultaneously creating a mosaic image with exceptional detail and motion detection capabilities. The level of visual sophistication seemed impossible for a creature that lived over 500 million years ago, during a time when most animals had not even developed basic eyesight. While many Cambrian organisms relied on simple light detecting cells or rudimentary eye spots, Anomalocaris possessed a visual system that would not be out of place in modern predatory arthropods. The evolutionary timeline became even more remarkable when researchers realized that compound eyes evolved before such features as a hardened exoskeleton and jointed appendages that define modern arthropods. This discovery showed that sophisticated visual systems developed before creatures evolved their distinctively hard external skeletons, fundamentally changing our understanding of early arthropod evolution. Patterson's research team demonstrated that this visual acuity surpassed almost every other Cambrian animal, providing Anomalocaris with an overwhelming advantage in the water column. The compound eye structure allowed for superior resolution and contrast detection, enabling the predator to distinguish between different types of prey and identify the most vulnerable targets. The hexagonal lens arrangement also facilitated excellent motion detection, allowing Anomalocaris to track fast-moving prey and respond to sudden changes in directional speed. These massive stalked eyes transformed precision hunting in the well-lit Cambrian seas into Anomalocaris' primary advantage. The elevated eye position provided panoramic vision across the water column, allowing the predator to scan vast areas for potential prey while remaining relatively motionless. The exceptional visual clarity meant that stealth attacks became nearly impossible for prey animals to execute successfully, as Anomalocaris could detect approaching threats or fleeing prey from considerable distances. The implications of possessing such advanced sensory equipment millions of years before other complex anatomical features appeared in the fossil record were staggering, while contemporary arthropods were still developing basic body segmentation and simple appendages. Anomalocaris had already evolved a visual system comparable to modern apex predators. This technological advantage in sensory capability preceded the arms race in defensive structures by millions of years, creating an unprecedented asymmetry in predator-prey relationships. This visual superiority transformed Anomalocaris from a simple predator into an ecosystem engineer capable of reshaping entire marine communities. The ability to see prey with exceptional clarity across different depths and lighting conditions meant that no niche remained safe from predation. Soft-bodied organisms that had previously relied on camouflage or simple hiding strategies found themselves exposed to a predator equipped with military-grade surveillance capabilities. The extraordinary visual system made Anomalocaris the ultimate Cambrian hunter, capable of detecting and tracking prey with unprecedented precision across the full spectrum of available marine habitats. But having exceptional eyes was only part of the equation. The real question was how this visually gifted predator used its physical weapons to capture the prey it could see so clearly. Those sophisticated appendages revealed a surprising vulnerability when subjected to rigorous scientific analysis. For decades, scientists assumed Anomalocaris used its curved frontal appendages to crush hard-shelled trilobites, but modern biomechanical testing revealed a fundamental weakness in this hunting strategy. The two massive grasping appendages, measuring up to 7.1 inches in length when extended, appeared perfectly designed for grabbing and crushing prey with their curved talons and flexible joints. This led to the popular interpretation of Anomalocaris as a trilobite crushing machine capable of breaking through the hardened exoskeletons that protected many Cambrian organisms. The appendages featured multiple segments connected by flexible joints, allowing for complex grasping motions and seemingly powerful crushing capabilities. Each appendage terminated in sharp, curved talons that could theoretically pierce or grip hard surfaces. The robust construction and substantial size of these structures convinced paleontologists that Anomalocaris possessed the mechanical advantage necessary to overcome heavily armored prey. Museums worldwide displayed reconstructions showing this apex predator using brute force to crack open trilobites like a prehistoric nutcracker. When researchers subjected detailed 3D models of these appendages to comprehensive analysis using kinematic and biomechanical modeling with finite element analysis and computational fluid dynamics, along with 3D digital reconstruction and modern analogues, the results contradicted decades of established thinking about Cambrian predation. The biomechanical testing revealed critical stress concentrations that would have made shell crushing both inefficient and potentially damaging to the predator itself. Rather than demonstrating the crushing power scientists expected, the analysis showed that the appendage structure was optimized for entirely different mechanical functions. Bicknell's 2023 study demonstrated that higher microstrain distribution along the thin, elongate endites predicted that the appendages were not reinforced sufficiently for exerting high levels of force onto prey. These finger-like projections along the inner edge of each appendage showed maximum stress values that exceeded safe operational limits during simulated crushing motions. The endites would have been damaged if used to attack biomineralized taxa, making sustained shell crushing extremely problematic for the predator. The biomechanical analysis revealed that attempting to crush trilobite shells would have been like trying to crack nuts with precision surgical instruments. Supporting this conclusion, only one specimen that shows such a putative injury has been documented among Anomalocaris appendage specimens, indicating these structures were not regularly used against hard prey. The appendages were actually optimized for rapid strikes and suction feeding in open water environments rather than the prolonged crushing actions scientists had envisioned. The flexible segmentation allowed for lightning, fast extension, and retraction motions, while the curved talons function more like precision grasping tools than crushing implements. The implications of this discovery fundamentally altered our understanding of how Anomalocaris functioned as a predator. Rather than relying on raw, crushing power against armored prey, This apex predator was built for speed, precision, and sophisticated hunting techniques that targeted vulnerable organisms. Computational fluid dynamics analysis revealed that the optimal outstretched posture of the appendages created minimal drag while maximizing agility in the water column, supporting rapid pursuit hunting rather than ambush tactics against slow-moving, heavily armored targets. The research revealed that Anomalocaris was primarily a soft-bodied prey specialist, using suction feeding techniques and precise grasping to capture organisms that lacked hard protective shells. The circular mouth, surrounded by plate-like structures, created powerful suction forces that could draw in prey while the appendages provided accurate positioning and manipulation. Rather than functioning as the indiscriminate apex predator, scientists had imagined Anomalocaris operated as a highly specialized hunter with advanced sensory integration and precision strike capabilities. This specialization would prove to have far-reaching consequences for the entire Cambrian ecosystem. Anomalocaris did not just hunt other Cambrian creatures, its very presence helped accelerate the first evolutionary arms race in Earth's history. The emergence of this 39-inch predator fundamentally altered the rules of survival in ancient oceans, creating selective pressures that had never existed before. Prior to Anomalocaris and other radiodonts, most Cambrian organisms lived relatively peaceful lives in marine environments where predation was limited to simple grazing or scavenging behaviors. As this apex predator prowled Cambrian seas with its advanced vision and precision grasping appendages, prey animals faced unprecedented selective pressure to develop defensive innovations. The sophisticated hunting capabilities of Anomalocaris meant that organisms could no longer rely on simple hiding strategies or slow movement to avoid predation. The compound eyes with their thousands of lenses could detect prey across vast distances, while the flexible appendages could capture organisms with surgical precision. For the first time in Earth's history, being soft-bodied and defenseless became a death sentence in the face of such an efficient predator. Organisms that had previously thrived in Cambrian ecosystems suddenly found themselves vulnerable to a hunting strategy they had no defenses against. The suction feeding capabilities and rapid strike techniques of Anomalocaris created an environment where only the most adaptable species could survive. The hunting pressure from Anomalocaris and related radiodonts forced rapid evolutionary responses across multiple prey lineages, driving the development of the first shell spines and protective armor in marine ecosystems. This process, called biomineralization, occurs when life creates its own minerals to form hardened structures. During this time, as animals began eating other animals more systematically, we see the evolution of hardened body parts as a defense mechanism against predation. Trilobites began developing thicker exoskeletons and defensive spines, while other arthropods evolved enhanced mobility and protective structures. Brachiopods developed stronger shell attachments, and various soft-bodied organisms began secreting calcium carbonate structures for protection. This predator-prey dynamic became a central engine of the Cambrian explosion, accelerating diversification across marine ecosystems in ways that had never occurred before. The presence of such an effective predator created intense selective pressure that drove rapid morphological changes in prey species. Within relatively short geological timeframes, entire lineages developed new body plans, defensive structures, and behavioral adaptations, specifically in response to radiodont predation. Anomalocaris functioned as an ecosystem engineer whose hunting behavior reshaped the evolutionary trajectory of early animal life. However, recent research suggests that while influential, Anomalocaris was very unlikely to have preyed upon calcified trilobites or other biomineralized taxa, which somewhat modifies the traditional arms race narrative. Instead, its specialization in soft-bodied prey created specific selective pressures that drove defensive innovations in vulnerable organisms. The presence of such an effective predator created niche opportunities for other radiodonts to specialize in different feeding strategies. As Anomalocaris dominated the role of precision, soft-bodied prey hunter-related species, evolved alternative appendage designs and feeding mechanisms to exploit different prey types. This niche partitioning among radiodonts led to diverse ecological roles, with different species functioning as raptorial predators, sediment sifters, and suspension feeders. Some radiodonts developed filtering appendages for planktonic organisms, while others specialized in bottom-dwelling prey or developed different suction feeding techniques. This diversification established the predator-prey relationships that would define marine ecosystems for millions of years following the Cambrian period. The arms race, accelerated by Anomalocaris, created evolutionary patterns that became fundamental to complex marine food webs. The defensive innovations developed in response to this apex predator formed the foundation for protective structures seen throughout the rest of the Paleozoic era. The shells, spines, and armor that evolved in response to radiodont hunting pressure became standard features of marine organisms for hundreds of millions of years. The evolutionary dynamics sparked by these predators established the competitive relationships that would characterize complex ecosystems throughout geological time. Yet the story of this remarkable predator reveals complexities that challenge our assumptions about ancient life. The scientific detective work that revealed Anomalocaris' true nature fundamentally transformed our understanding of Cambrian ecosystems and the origins of predator-prey evolution. Modern technology replaced simple fossil fragments with a sophisticated picture of how Earth's first apex predator operated using finite element analysis and computational fluid dynamics to reveal biomechanical truths that traditional paleontology could never uncover. This research showed how precision instruments and advanced compound eyes replaced brute force assumptions about ancient hunting strategies. The discovery provides crucial insights into arthropod evolution, helping scientists understand how characteristic features like compound eyes and specialized appendages first developed in early marine ecosystems. However, even this remarkable predator could not survive forever. Radiodonta disappeared from Earth 485 million years ago at the end of the Cambrian, victims of oxygen depletion, glaciation, and volcanism that reshaped marine environments and ended their evolutionary dominance.